So let's discuss the third problem of today's weekly contest, maximum candies allocated to k children. So we are given an array of candies. Each element of the array represents a pile, and we can split this pile into any number of piles that we want. And we are also given an integer k, which denotes the total number of children that we have. We need to split these piles and give one pile to each children, and such that the total number of candies that each children get is maximized. And the constraint is each children should get exactly same number of candies. So for example, if we have these three piles, 5, 6 and 8, we can split this pile of 5, uh, we can split this pile of 6 into two piles, one of 5, another one of 1, and we can split this pile of 8 into two piles, one of 5 and another pile containing 3 candies, and then we can assign this to the first children, this to the second children, and this to the third children. So each children receive exactly one pile, and each children gets exact same number of candies, and we can't do better. So every children will get maximum 5 candies in this situation. So that's the answer. Now, what makes the problem difficult? Let's say uh, we what we can do. Let's say we split this candies of 5 into 5 piles, each of size 1. Similarly, we can split this candies of 6 into 6 piles, and this candies of 8 into 8 piles, each of 1. Okay. Now, uh, after doing this, we will have 19 piles of 1 candies, and then we can start merging them. So we have 3 children. We will just divide 19 by 3. We will get 6. So basically we will just uh, accumulate first 6 piles, and then second 6 piles, and then third 6 piles, and so on. So each children will get then 6 candies. That's the maximum. But we can't do this because it is written that we are not allowed to merge. So we are not allowed to merge two piles together. So this makes the problem a little bit harder. So let's try to solve this version of the problem. So first, let's try to understand. Let's say we want to find whether we can give, whether it is possible to give X number of candies to each children or not. In the same question, like there are three children. Like we will assume there are k children, and we want to distribute we want to give each children x number of candies. So for this problem, let's say x equals to 3. So we just need to find out whether it is possible or not, yes or no. Okay. So how to solve this problem? So what we want to give every children a pile of 3, right? So it doesn't make sense to have a pile greater than 3. So let's start splitting every pile into piles of 3. So we will first start splitting this 5 into piles of 3. So we will get two piles, one of 3, one of 2. Start splitting this 6 into piles of 3. We will get two piles, each of 3. Start splitting this into piles of 3. We will get 3 piles, two of size 3 and one of size 2. And now we can see we have total 4 piles of size 3, or basically size x. Now, sorry, 5 piles of size x. Now if k is less than equals to 5, then we can say that okay, it is possible to give every children piles of x such that they receive exactly one pile, and their number of candies that they get is 5, is x. So but if k greater than 5, like number of children is greater than the number of piles of 3 that we have, then we can say that okay, it is not possible to split this uh, given piles of candies such that uh, each children gets one pile and each will get x number of candies. So hope this one is clear. So let's just try to look at the sample algorithm. So basically, what we have is like we want to write f of x, which which will say whether k children have x number of candies or not. Now for each pile of I, we know that total possible splits of size x will be this I by x, and if total possible split of x is less than equals to k, basically we have less children than total possible splits, then it is possible to allocate them each a pile of 3 or pile of x, otherwise it is not. So return true, otherwise return false. So now having found that, like, now we know uh, how to write f of x, which basically denotes whether it is possible to give every children a pile of x or not. Now what the problem now reduced to, we will just start with 1. We will start, like, we will call f of 1. If f of 1 is true, it means we can give one if we can give every children a pile of 1, then we will calculate f of 2. If it is true, it means we can give every children pile of 2, 3. If it is true, f of 3 is true, then we will move forward with 4, then we will move forward with 5 until f of x is not true. So when, let's say, f of 5 is not true, then the answer will be 4. So basically we will just move forward and then call this f of x function every time, and whenever it return false, we will have the answer. Now we can't do this because this will take, like, calculating f of x, if you remember, will take order and time. Like, we have to iterate over all the piles. Okay, so it will take order and time. And if we just search linearly uh, in this manner, it will again take order and time. So it will not be a it will not fit in the time complexity of the problem. So then what we can do, like, again, this is a searching problem, and as we did yesterday for the biweekly contest, the same concept apply here. It is searching problem. We have to do better than linear search. So the first thing that should come to your mind is binary search. So what binary search is basically, given the sample space, you will just go to the middle of the space and just see whether you can skip either the left or the right part of the array. So if you can skip any one part of the array completely and search in the rest of the array, it means you can apply binary search. So in our question, let's say this is the possible split, like this is the one split. Now we are saying that the statement is true up till this split. What's the statement? Statement is we can give every children a pile of 4. Then would it make sense to search in the left part of the array anymore? No, right? Because basically if we can give every children a pile of 4, then we can definitely give every children a pile of 3 and a pile of 2 or a pile of 1, right? So it doesn't make sense to search in the left part of the array anymore. We will just skip the left part and search in the right part of the array. Similarly, if f of 4 is false, basically we can't give uh, every children a pile of 4, then it doesn't make sense to search in the right part of the array. Why? Because if we can't give every children a pile of 4, no matter what, we will not be able to give every children a pile of 5. So we will just go and search in the left part of the array. So hope the intuition is clear. So basically, we know how to write f of x, and we just need to do a binary search on the search space. So let's look at the solution. So this is the left and right bound. So each children can get at in the minimum 0 candies, and at maximum they can get 10 to the power 7 candies, because let's because one split can be of at max 10 to the power 7. Now, while as L less than R, like, this is, we are going to the middle of the array, and this is what we have, our f of x, right? So basically, we are just calculating how many children can get m plus 1 number of candies, and if this is greater than k, then it means that we can split m plus 1 candies among k children. Then it doesn't make sense to search in the left part of the array. So we will just move our lower bound to the middle of the array, because we just want to skip the entire left. So we will just move our L to this. Similarly, if it is not possible to split, like if k is greater than the number of splits of m plus 1, then we will just search in the left part of the array. So hope the solution is clear. If there is any doubts, please ask them in the comment section below, and I will happy to answer. If you like the content, please like and subscribe to the channel. I will see you next week. Thank you.